So, hello. I'm going to talk about a tool that can convert your Gaussian error model to some T-type error model, or a mixture of Gaussian and T-type error model. Actually, this is the original title. There was an accurate inference via a mixture of Gaussian and terrors. One day, Suji emailed me saying, "Oh, your title seems weird." And I checked my title, and it seems weird too, neither. So I corrected this title, but I recovered here because I like this title. This is joint work with Justin Ellis, and thanks to him, I could get into this statistical model. So I confirmed that most of you are using Gaussian error models. Maybe that's because this is convenient mathematically, computationally, or some theoretically. However, this Gaussian error model, although it can be efficient without outliers, it can be very biased if there exist outliers. Student T error has the opposite pros and cons. The inference becomes robust, but it can be less efficient because you are assuming heavy tail error assumptions to most of Gaussian data. So then my question is, then why not use both? So that this mixture error can complement the pros and cons of both error models. So with some probability, it becomes Gaussian error, and with other probability, it becomes T errors. So this is the mixture error model that I'm proposing. So the first line is basically your Gaussian error model, and I multiply alpha sub j, whose power is zj, to the known variance component. Vj is kind of your measurement variance, the known measurement variance. So zj is a latent outlier indicator that becomes 1 if the model considers this datum as outlier, or 0 otherwise. And theta j is the probability of datum j being an outlier. And alpha j is called an auxiliary variable that expresses T distribution as a scale mixture of Gaussian and inverse gamma distribution. It can be tricky, but so I prepared one example. Suppose this random variable x follows a Gaussian distribution whose variance is alpha. And alpha follows an inverse gamma distribution whose shape and scale parameters are equal to nu over 2. Then, if we integrate out alpha, then marginally, this random variable x follows a T distribution with nu degrees of freedom. This is well-known fact in statistics. The history is quite long. Okay? And this proposed mixture error is marginally equivalent to a Gaussian error model if the outlier indicators are fixed at unity. And it becomes a T error if the outlier indicators are fixed at unity. Or maybe I talked previously. And also this proposed error reduces to the targeted, the mixture of Gaussian and T error. And finally, this mixture error reduces to a mixture of two Gaussian errors with different variances if this auxiliary variable alpha j is fixed at a constant, or maximum likely estimate. And this is recently adopted in astrophysical journals. And I think astrophysicists like this approach. I mean, modeling outlier with two different Gaussian distributions. But statisticians like T distribution for modeling outliers. So my attempt was to make a bridge between these two models so that we have more flexibility between Gaussian or T errors. So my interest was about some easy tool to convert any Gaussian error model to a mixture model, because this mixture model can be 100% T error or a mixture of Gaussian or T errors. So the conversion is actually quite simple. Suppose this is what you are using in your model, the Gaussian measurement error model. And I'm just multiplying this modification term, like alpha g to the zj, to the known variance components. And I set up some prior distribution to account for the uncertainties of these extra parameters. So that's it. And implementing this mixture error model is also very simple. What I need is your sampler based on Gaussian error model. If you give me your Gaussian error model sampler based on Gaussian error model, I will modify your sampler by replacing the known variance component with this modified variance component. And at each iteration, after I update your parameter of interest, I will update the additional parameters. So the conversion is not that difficult. So any Gaussian error model can be converted into mixture of T error and Gaussian error models. So I prepare a simple example, and the example from just the collaboration with Justin. So I generated 3 data sets. The first one is composed of the 20 realizations of a standard Gaussian distribution. And the second and third one are the same as the first one, except the last observation is incorrectly recorded as -10 or 10, just to make a synthetic outlier. So I set up 3 models. The first one is a Gaussian error model, which is the same as a regression with an intercept term. There is no covariate. And the second one is T error model, which is recommended by famous statistician. Here, error follows the T distribution with 4 degrees of freedom. And I obtained this mixture error model by just multiplying this term to the variance component. And I set priors because this is not fixed constant. We need to account for some uncertainty of these additional parameters. So here is the result. The second panel is from the data without outlier. So without outlier, the Gaussian error model, the black dashed curve, has the highest peak near the true value as 0. This makes sense because we are assuming Gaussian error model for Gaussian data. If you see the solid red curve, which is from T error model, this curve has the widest spread. Because we are assuming, because this assumption says, this assumption imposes unnecessarily heavy tail assumption on Gaussian data sets. So you are losing some efficiency by mismatching the error models. So a mixture model is expected to produce a curve that passes in between the other 2 curves. Because mixture error model is a weighted average of the Gaussian error and T error models. Without outliers, the dotted blue curve is expected to pass in between the other 2 curves. But in this case, because the data are Gaussian, the dotted blue curve moves close to the distribution from Gaussian error model. So let me call this is a mixture effect, the weighted average. Without outliers, this curve is expected to pass in between the other 2. When there exists outlier, the Gaussian error model, denoted by the dashed black curve, deviates from the truth severely. But the robust error models, for example, t-error or mixture error models, stays at the previous, maintains the mixture effect robustly. Because of this mixture effect, in the presence of outlier, the mixture error model leads to more accurate inference on the parameter value. So the cost of this mixture error model is the CPU time, because based on your Gaussian error model, I'm updating the extra outlier model parameters. So in this case, the Gaussian error model is like 1 second, less than 1 second, but you are spending 27 seconds for running mixture model. So there's no free lunch actually. But if the computational source is not your concern, then this is worth for checking the Gaussian error model your Gaussian error model. So I prepared a video from which I understood the science behind PULSAR data analysis. I know that most of you are astrophysicists, but because some of you are statisticians, hopefully this will help you understand PULSAR timing data analysis. Okay. Okay, video doesn't work. Okay, let's give up. The science behind PULSAR data analysis was explained by Justin earlier, so let me continue his model.
Actually, in the real signal, it will play.
Yeah, it should work.
I think I'm fine. I'm fine. Oh yeah. Oh, cool. So 2 galaxies are merging here. And inside these 2 galaxies, 2 black holes are interacting with each other. So this interaction between 2 black holes generates the low frequency gravitational waves.
There might be a sound.
There's no sound.
There's no sound.
Yeah, it's fine. Yeah. So gravitational wave is denoted by this wave on the green surface, coordinate surface. And this gravitational wave propagates towards our galaxy. And within this galaxy, there's a pulsar and the Earth. Pulsar, the light curve in the universe, sends pulses to the Earth in a very regular fashion. But because of this gravitational wave background, the arrival time has some deviation from the exact clockwise regularity. So I think astrophysicists are using this deviation from regularity to investigate the gravitational wave.
Play 1 second.
Can you come back to my slide? Yeah, this one. Sorry, it worked perfectly well in my laptop. So this is the model Justin earlier just described, and I denoted these figures into some mathematical formula. So there are many factors that affect the time of arrival of pulsars. And the beauty of his model, actually this is a description of his model from statistician's perspective. So the beauty of his model is that he modeled all these factors into 2 Gaussian distributions. So white error noise follows a multivariate Gaussian distribution with known variance component n. which is diagonal, and the diagonal elements are measurement variances. And for all these components that affect the arrival time, he used a multivariate Gaussian distribution that uses a spectral approximation to the covariance function. I think this is what Suji talked in the first day. I mean, using some basis approximation to the covariance function. So based on his model, we can derive the probability distribution of the observed residuals. So residuals follows a Gaussian distribution with some variance component from white noise and the other variance components from the other factors. And actually, this matrix T is quite complicated, and B is also quite complicated because that uses some physical details of these factors. And he modeled this B matrix as a function of parameter phi, which is the amplitude of the spectral density function, and gamma is the exponent of the power law of frequency. And based on this model, we can write down the likelihood function. And fortunately, he was using proper prior distribution. So I know that posterior is automatically proper. And actually, what he does is to derive a hierarchical model using the marginalized distribution. And what I did is simply multiplying this alpha to the z term to the known variance component. And I set up some prior distribution for the extra parameters. So here is the example of simulation study. Actually, our collaboration is quite interesting because, as I told you, what I need to know was his sampler. If I know his sampler, then I can just build an add-on to convert his Gaussian error model into a mixture error model. So I wanted to know his sampler, so I asked him to give me the code. So he gave me the code, but it was written in Python, which was black box to me because I didn't know the Python. So I translated the Python code into R code. And then from there, I added this component. And I gave him an R code. So I think he had a hard time to translate that R code into Python code again. But based on that, we could understand. And I think right now, Justin can implement this model in a more complex model to analyze real data. So this is one of the tests he did. And the blue dots are the simulated, the residuals, the time of arrival minus the timing model. And each dot has some uncertainties. And the orange cross, the yellow crosses are the synthetic outliers he generated. And the red dots are the data point that our model consider as outliers, or the data points that our model considers that T error is more appropriate than Gaussian error model. So we did some sampling using the previous existent model and our new models, checking several error assumptions for the same Gaussian model. So the three left panels shows the result from Gaussian error model, but one is from the original model based on marginal likelihood. And the orange curve shows the result from Gaussian error model, but in this case, we use hierarchical model. They actually should be the same, but since the sample sizes are different and we didn't normalize it, it has some difference between in height. But actually, these are the same. The results should be the same. When we use T error or mixture error model, the results are quite different. So in this case, the distribution for each distribution of each parameter contains the true generative value near the mode of each marginal distribution. So our joint distribution catches the true values of parameters near the center. But actually, although we didn't plot these in the same scale, this mode is actually around here. It shows that if you use Gaussian error model, your inference can be highly biased, missing the true, couldn't recover your true value. So this is our one result, and it was a very interesting figure. So on the data set, we displayed the fitted mean value of the curve. So the orange curve is based on Gaussian error model. And the green curve is based on our mixture error model. As you can see, the orange curves are trying to fit all the data point fluctuating and try to fit that outliers, and it moves very, it fluctuates a lot. But because our mixture error model accounts for those outlying observations, our green curve is fairly smooth. I mean, robust to these outliers. Any questions? Okay.
It's like, so the error model catches the actual values, but so that if you don't include the error, your model still have a secondary peak around that value. You said it was degenerate, right? So
Oh yeah, yeah.
Gaussian model, only you have at least a secondary peak in the area of the actual value.
So whether Gaussian model contains...
Because you said it was down there.
Yeah, it's around here.
But you said it was also degenerate, so there was another solution.
No. There is just one generated parameter values, which is this, which were indicated by this blue curve. But if we add some thin-dirty outliers, and if we fit our Gaussian error model, the result will become around.
There was no multimodal.
Yeah, this is not multimodal situation. So each error model produces univariate joint distribution. But if you use Gaussian error model, then your inference can be highly biased here. Question?
You have a situation where some of the outliers actually have, are better estimated. Is there a way to account for that in this model?
This model does not account for that automatically. What it does is to downweight, a way to downweight the outlying observations in terms of estimating the parameters. So those outliers doesn't contribute to our parameter estimation because we downweight it by a T-error model.
Yeah, that's great. It's just that I have a problem in mind in which there are multiple measurement points, but some are estimated better than others. But the ones that are estimated better could actually be conceived as outliers.
Yeah, I think in practice, there are two cases. Like, one is very outlying but high measurement errors. In that case, maybe we can consider it's just one standard deviation away from our overall mean. The other case is some outlying point with very small measurement errors, which can be problematic. But in this case, we are trying to downweight. It's kind of the effect of removing that point in terms of estimating parameters. But removing data point without any reasonable reasons makes statistician uncomfortable. So I think this is one way to keep all the data points to make an inference, which is accurate and robust.
No, I was just wondering that if you go back to the earlier plot, so here the number of outliers is much, much smaller than the actual data. But if you have a much higher proportion of outliers in the data, would this mixture error model still work as effectively to identify those outliers?
Yes, I think Justin this morning, Justin tested the dirtiest data, the real data that many astrophysicists gave up to analyze. And it was successfully account for most of outliers as fitting T errors, I think. It was, yeah. I couldn't prepare that example because it was just done this morning.
Question, like, I mean, if you knew what the outliers were, so why you are bothered? I mean, after this, your method detects the outliers, and how do you feel confident those are the ones that are the outliers? And if that is the case, that you knew the outliers before even fitting the model, why bother fitting the model?
Although we generate synthetic outliers, we didn't assume, when analyzing this contaminated data, we didn't assume that we know the outliers.
But did you generate the outliers using the T, or you just, I mean, in the first example, you said that let's fix something at -10 or 10, but those are not really generated from the T. Because the T you are using 4, which has a variance of 2, that the most largest value would be 2 times 4, 8. So 10 would not be observed even from the distribution.
Yeah, I think we also had some simulation for that purpose, like generating all the data from T distribution, not Gaussian distribution. And even in that case, it was quite robustly successful, I think.
Okay. Yeah, this example is just the first test case I did on this, just to see if you could do it. And all I did was these are just from a different Gaussian with a much bigger variance. But I did do ones where you just, no, but I did do ones where you simulate from T and they do that. I've done ones where you simulate T plus those and it all works. But the thing is that these are all nice because you can see them easily by eye. But in real data, usually you can't see them by eye. And also, like in my talk, there's that timing model, and the timing model has lots of parameters, and there are things in there that will hook on to sort of outlier things, and it'll just bias the rest of your parameters. So you might not even see it when you're just looking at the residuals, because remember, in the model, we're basically putting the timing model piece back in and yeah. Yeah, well, I mean, there just could be some like this. All we did was to just picked, when the mean of that z parameter is greater than some value. But if you're modeling it all through, you don't really care if they're outliers. You just care about the inference on the other parameters.
Yeah, because... Great. Oh, you mean bias in one direction? I think I tested that in the first line, in the first example. So this is just one way outlier. It may move, but because the key of this model is to downweight those outliers, the inference will be based on some normal data, the data whose errors are assumed to be Gaussian, but for the data point assumed to be T will not affect our parameter estimation in a greatly.
But if it is actually binaural.
Comes to then what is data and what is outlier.
Yeah, actually, when we develop this model, outlier detection is byproduct. The main focus was whether we can make an accurate inference in the presence of outliers.
Case, I mean, if
your main goal is to not detect outliers, but to make inference about the signal when in the presence of outliers, I mean, there are lots of these robust regression methods which are based on, say, L1 or other norms, not the Gaussian L2 norm. That automatically eliminates those problems. You don't have to even model it. So in this problem, if I use the median, it doesn't matter what error you put, it will give you best estimate.
Oh, yeah, that's also possible. But one direction that I'm setting was to have a simple tool to convert the Gaussian error models.
That's a different goal. But if I was saying, if your goal is not to detect outliers or model the distribution, but to recover the signal in the presence of outliers, there are robust regression methods like L1 regression and or other type of robust regression methods, which automatically takes care of those problems of outliers without identifying which are the outliers.
Yeah, I acknowledge that there are possibly many ways to downweight the outliers in making an inference. And I think that is one way, and this is just another way. Maybe this model's advantage is for computational.
Computationally, it is simpler than L1 estimation. Trimming is another utility you can use.
Oh yeah, I think some astrophysicists are just removing out some outlying data point based on some specific criteria.
Which may or may not be the right thing.
Yeah, I mean, nowadays there are methods like lasso and things like that, so which are based on this kind of linear programming methods, which are extremely fast with high dimensional, which uses L1 norm. So this was not present before 1995 or so. So now those methods are available, and these are extremely fast methods. I mean, it would be worth comparing yours to them. I'm not saying that this has many other advantages that the other methods will not have, but if the goal is to just detect the signal in the presence of outliers, it would be worth comparing to yours.
Thank you for mentioning lasso.
I was just going to say, I'd be interested in that too, because and I think this is because, at least our group in general, like all we know is Bayesian stuff and MCMCs. That's all we know basically. And so every time we try some other like standard statistical thing, there's always some assumptions that are either our likelihood or our data just breaks. So if there are other ways of doing this that actually will work, then that would be good too.